shaped by the collision of previously separate areas of continental rock and has moved across the surface of the globe twice to both the north and south polar regions. Australia has experienced enormous changes. Its rocks have crumpled, melted and been uplifted, eroded and redeposited. Its climate has varied dramatically, and it has seen a continuously changing procession of life forms as evolution has altered them into ever more varied and complex types. With the passing of time, it has developed the unique heritage we enjoy today. The origin of our planet was so long ago that much of the evidence for it has been lost. Born like the other planets from the gas and dust of the early solar system, planet Earth gradually cooled and was soon covered by oceans of molten rock and rafts of solid matter. Condensation of the surrounding gas cloud produced water. The rocks of the original crust were produced by volcanic eruptions from the partially molten mantle. Meanwhile, the interior of the planet was forming. Iron and nickel sank to the core, while the lighter elements rose to the surface.
We know the types of rocks that make up the Earth's mantle because some particular types of volcanoes bring up fragments of the mantle. For example, this is a fragment of the Earth's mantle which has come from 60 kilometres below the surface of the Earth from Western Victoria. The black part around the outside is some of the frozen magma that has brought it to the surface. It's very important to do this type of research because these rocks are a unique window into the composition of the interior of the Earth. Some samples represent the pristine composition of the Earth as it formed from the solar nebula 4.6 billion years ago, and other samples, such as this particular one, give us an indication of the sorts of changes that have happened to the Earth throughout its geological evolution throughout those 4.6 billion years. This is a view through the microscope of thin sections of rocks which make up the Earth's mantle. These thin sections give us a glimpse of the microstructures of the rocks that make up the mantle, of the forces that they've been subjected to throughout geological time, and the bright colours help us to determine the types of minerals that make up these rocks.
Modern methods first developed at the Australian National University have enabled us to date some of the minerals contained in these early rocks.
The oldest known terrestrial material is zircon crystals, which are found in this sedimentary rock from Mount Narrowere in Western Australia. Zircon crystals are tiny fragments of zirconium silicate, extremely small. And when zirconium silicate first crystallizes, it takes in uranium. That uranium then decays to lead, and we can measure the uranium and the lead and work out the age of the crystal. This is called the shrimp iron microprobe. What we do is we mount the zircons up and we put them into the instrument where they are ready for analysis. We take them down into the main receiving chamber, and then we fire a high energy beam of charged particles at that target. When the particles hit the target, they remove small amounts of material, and that material is then accelerated at high voltage into the rest of the machine, and that it can be measured for chemical and isotopic composition. Here we have zircon crystals which show the structure of these small grains. Zircon crystals grow from the centre outwards, and in the middle of the grain you have the oldest material. On the outside you have layers of younger material. With the iron microprobe we can date the centres and the outside separately. These are not the only old rocks in Australia. The highly coloured silica-rich rocks at Marble Bar are remnants of old seafloor.
Rocks at Mount Narrowere and Marble Bar are very rare examples dating from the first 1,000 years of Earth's history. Life forms first appeared on Earth some 3,500 million years ago. The shallow waters around the thousands of emerging islands were full of dissolved chemical compounds, especially carbon, the essential element for life. The Earth was an inhospitable place at this time of the dawn of life. The the crust and the seas were hot. The thin atmosphere was a toxic mixture of hydrogen, ammonia, methane and carbon monoxide, with little or no oxygen. Ultraviolet radiation from the sun was lethal except underwater. In the primordial soup of the shallow seas, the first reproductive life emerged in the form of single-celled bacteria and blue-green algae. Stromatolites are dome-shaped structures formed by some blue-green algae secreting calcium carbonate and accumulating fine sediment below their living bacterial mat.
It seems life first appeared on Earth something like 4,000 million years ago. At about that time, the temperature of the Earth's surface stabilised to a point where the organic chemicals that were the necessary precursors of life could exist. Not too cold, not below 0 degrees so that they wouldn't freeze, and not above, say, about 50 degrees centigrade so they wouldn't roast. And from these organic precursors, life evolved. It seems that life was created only once. It doesn't seem to have happened since. And it must have happened somewhere away from the surface of the seas, because at that time ultraviolet light would have been toxic to light. And a possible location is around hot springs on the ocean floor, where in fact life exists today in a system driven by energy from the Earth and not by photosynthesis driven by the sun's energy. We know this because very rarely we find actual life forms from this period preserved as fossils. We also know it because within the genetic material of things living on the face of the Earth, we see definite stages of evolution, and by comparing the genetic material of living things, we can get an idea of how they evolved and what they evolved from. But I think most importantly, the early life forms have left evidence of the way they existed in the forms of large structures that are preserved in the rocks. So although the life itself was microscopic, their lifestyle led to the creations of objects in a sort of way similar to early civilizations leaving lost cities, if you like. And it's these structures, the stromatolites, that give us a great deal of evidence of what life was like on the surface of the Earth at that time. As soon as life appeared, it was able to interact with the environment. And until that time, everything had been controlled by chemical and physical processes. And now we had the introduction of biogeochemical cycling. And perhaps one of the most dramatic examples of this was when the microbes eventually got into a situation where they were being driven by energy from the sun, photosynthesis was taking place, and oxygen began to be given off. And this gradual evolution of oxygen had a dramatic change, first of all in the seas and then in the atmosphere. And eventually it led to the point where the atmosphere became as it is today, and the oxygen in the atmosphere could support the evolution of still more complex life forms.
About 2,500 million years ago, the arrival of other chlorophyll-containing organisms seems to have triggered the deposition of a vast amount of iron oxide. Relics of these thick sediments occur in the Hamersley region of Western Australia. Dissolved iron combined with oxygen to form particles of solid iron oxide, which slowly built up on the sea floor. Eventually, by 1,800 million years ago, the seas had been cleared and dissolved of iron as they remain today. The seas at this time did not cover the entire surface of the Earth. The remaining landmass consisted of large, stable areas of ancient deformed continental rocks called cratons.
A craton is an area of ancient continental rocks which have been stable for a very long time. There are several examples in Australia, for example the Yilgarn and the Pilbara blocks in Western Australia. And the reason why they're very important to study is that they contain the oldest geological record available to us, and by looking and studying this by various methods, we can work out a lot about very early Earth history. And I have several pieces of rocks to illustrate some points of study of cratons. Here is a piece of gneiss from Western Australia, from the Yilgarn craton. It's called Meabury gneiss, after where it came from, and you can see it has a banded structure. The grey stuff in here is very old, about 3,700 million years old, and as such is the oldest bit of Australia still in existence. We have these pink bands running through there, and they are granite. They're considerably younger, about 3,300 million years younger, and we're intruded into this early continental nuclei that we find in Western Australia. I have two other pieces to look at. I have this piece of quartzite here, which is very ancient. It is about 3,800 million years old, and it is important because this shows that at that time there was already water on the surface of the Earth in order to wear away and form sedimentary rocks. I also have this large piece here, something called a norphosite, which is an igneous rock. And by looking at this kind of rock, we can find out not only things about the Earth's crust, but from its chemistry, things about the Earth's mantle underlying the crust.
By 1,000 million years ago, the various cratons were welded together as one unit. This forms the western two-thirds of the Australian landmass as we know it today. However, there was one major difference. Continental areas that later became India and Tibet bordered Australia to the west, and Antarctica bordered it to the south. This great southern continent was called Gondwana, and this was the beginning of an association of land masses that would shape both the form and the distribution of much of Earth's life. By this time, the seas, including those that washed over much of Central Australia, contained a new, more complex kind of cell, which was eventually to give rise to all the great diversity of the world's plants and animals. $750 million years ago, the Gondwana landmass was subjected to a major period of glaciation. A belt of ancient glacial deposits is evident from the Kimberleys in Western Australia to the Flinders Ranges in South Australia. This was the Earth's most devastating ice age, for Australia was not even in the polar regions, but lay somewhere in the northern tropics. In the wake of this glaciation, cellular life forms gave rise to a further diversity of soft-bodied marine animals. These are preserved in 600-million-year-old sediments in the Flinders Ranges.
We're talking about a period of Earth history when there were quite revolutionary changes in the surface environment of the Earth. The most severe glaciation that has ever affected the Earth has just finished, and partly as a result of that, the composition of the atmosphere was changing enormously. For instance, the greenhouse effect, far more severe than any current greenhouse effect, was decreasing rapidly, and in addition to that, the amount of oxygen in the atmosphere was increasing. Those various environmental changes were probably the triggers that, in some ways that really aren't well understood, started early animal evolution. The evidence that we have of that is in the form of fossils, such as the ones we have here. These come from a place called Ediacara, a little range of hills near the Flinders Ranges in South Australia. And ones like this, for instance, this was interpreted originally as a complicated jellyfish. It may not be that, it might be another sort of animal, but quite a complex one. In addition, we have fossils such as these. These are flat worm-like animals of some sort. They grow up to a metre long, so these are relatively small examples. All of these and other sorts of animals occur in sandstones. And here's another example of a jellyfish-like fossil. So there are many such fossils as these from Ediacara, and in fact from many other locations around the world. And that's the evidence that we have of early animal evolution.
Just after the appearance of the Ediacaran fauna, the final assemblage of the landmass of Gondwana occurred. It was accompanied by such compressive forces that the central region of Australia was deformed into a major mountain range. Sedimentary material eroded from the newly created mountain chain was spread across the continent from west to east. These extensive sediment layers were later deformed into a series of folds, which extensively eroded, leaving a few spectacular relics including Uluru and Gugacha. As multi-celled animals diversified, soft-bodied creatures were replaced by animals with hard outer skeletons. A revolution in the life forms of the Earth began, and with it, the fourth stage of Australia's geological development. First primitive backbone animals eventually gave rise to some 1.5 billion species of vertebrates. Meanwhile, along the eastern seaboard of Gondwana, new plate movements occurred over a 4,000-kilometre front. The oceanic plate began to plunge beneath Australia and Antarctica, resulting in the addition of a new eastern craton. Island arcs, oceanic plateaus and continental crustal fragments were pushed against the continent. During this process, referred to as terrain accretion, eastern Australia experienced major upheavals accompanied by volcanic activity. On the northwest margin, several pieces of Gondwana were removed to Asia. But other areas have remained far more stable. A spectacular coral reef developed some 370 million years ago in the Canning region and can still be seen today, fossilised but undeformed. Meanwhile, an even more dramatic event was unfolding. Life was emerging from the sea for the first time. Marine blue-green algae, the ancestors of all higher plants, had by now reached a stage of considerable diversity.
The blue-green algae certainly was successful, as were other aquatic plant groups, including the green algae and the brown algae. Land plants are thought to have derived from the green algae, which were clearly photosynthetic and therefore manufactured their own food. This is an important point to establish before moving on to the land. But to go from the land to the water, the plants needed some structure to support them. And so they had to develop conducting tissues and eventually root systems to hold the tall plants that we know today. The simplest land plants arising about 420 million years ago were like the one I'm holding here. You can see that they are no wider than 3 to 4 millimetres wide and perhaps growing to 0.5 metre. Now we're fortunate today to have a very similar form still living after 420 million years, and it's called Psilotum. There's a wonderful pot of it just here. This plant has no leaves, although it's very green. It is photosynthetic, so it manufactures food from the sun and carbon skeleton. It has no root system. It has underground branches with small hairs holding it into the ground. Its reproduction is by these small spores that occur in these spore sacs here. The spores fall to the ground and develop male and female components, and sperm from the male fertilises the egg and produces another plant.
By about 350 million years ago, the descendants of these simple land plants had achieved two great evolutionary advances. They increased in size and developed the ability to form seeds. Australia lay at approximately the same latitude as today, but before long, continental drift was once again reactivated. The landmass journeyed some 5,000 kilometres to south polar latitudes. For 80 million years, much of its area was entombed beneath an extensive ice sheet. This long, frigid interval had a major impact on the plant life of Australia's ice-free areas. Tree ferns are the most notable survivors from this time. They have changed little and still flourish today in our cool southern and highland forests. After the Ice Age, the climate warmed and there was rapid evolution of a rich flora. Extensive cool temperate swamps with thriving plant communities formed coal deposits. Early conifers and ginkgos, or maidenhair trees, appeared in the fossil record. The most common and widespread fossil plants of this coal-forming period were Glossopteris, which dominated the vegetation of the whole Gondwana landmass at this time, and may have been the ancestors of modern flowering plants. Around 200 million years ago, the climate became increasingly hot and arid. Dinosaurs, like the awesome Eranchiosaurus and the savage carnivore Tyrannosaurus, ruled the planet. This pattern remained largely unchanged until about 65 million years ago, when a major global catastrophic event wiped out 3/4 of all known life forms. All the dinosaurs and many other species were swept into the fossil record.
Extinction of the dinosaurs is thought by many scientists, but not all, to have been owing to the impact of a comet or asteroid about 63 million years ago. Evidence for the impact site of this event has recently been found on the Yucatan Peninsula of Mexico. In Australia, we have no record of this, but we have a contribution to make to this controversy in the sense that dinosaurs here were living through the winter because southeastern Australia was very close to the South Pole. They were living through the conditions of nuclear winter for at least a few months every year. So if the scenario that's been brought up by many scientists that as a result of the impact there was a dust cloud, the temperatures got very cold, was true, you have to constrain the time. It has to be much longer than just a few months because we know dinosaurs were capable of doing this every year. The extinction of the dinosaurs was not the most widespread extinction that happened on Earth. We know of others. For example, 250 million years ago, almost 90% of all the living families of invertebrates in the sea at that time became extinct. So that was a much greater, much broader extinction than what happened at the end of the Cretaceous period when the dinosaurs died out. Now, was this extinction a totally negative event? Well, possibly not. It may well have paved the way for other groups of animals to evolve once the dinosaurs were gone. In particular, it may have paved the way for the mammals, of which we are a member. So thus, that asteroid or comet impacting the Earth may be the reason you and I are standing in this room today instead of some dinosauroid who evolved to be intelligent.
By the time that this extinction episode occurred, fragmentation of Gondwana was complete. Seafloor spreading had separated Australia from Antarctica for the first time, and had also isolated New Zealand. By 38 million years ago, marine barriers were wide and well developed. Australia had become the island continent, its plants and animals now isolated from those of other continents. Coinciding as it did with the fragmentation of Gondwana, the extinction event cleared the ecological stage for a new burst of evolution. The separation of the continents allowed Australia's isolated animal and plant populations to evolve and diversify without interference from immigrant species. Free from the dinosaur shadow, mammals came into ascendancy. As the Australian continent then drifted north, the climate became drier. Australian mammals reached their greatest variety about 25 million years ago, as grasslands started to spread. Many plants and animals that were unable to adapt died out. Another factor that filtered out the survivors was the need to withstand the fires that began to ravage huge tracts of land. One of the most interesting effects of the northward drift of the island continent was its collision 25 million years ago with an Asian island chain in the north. This collision produced the spine of the New Guinea highlands and large submerged areas in the Torres Straits and the Gulf of Carpentaria.
15 million years ago, Australia crashed up into Southeast Asia. The result of this was New Guinea, for the first time, really, rose above the sea. The oldest rocks in New Guinea are 15-million-year-old marine limestones in the highlands. Now, what that meant was that in a world struggling for fresh water, Australia was going to get even less because it acted as a rain shadow. Water-laden winds that would normally come sweeping in across northern Australia in these sort of sub-equatorial zones were stopped by New Guinea, and Australia began to dry out. But it wasn't all total disaster because some sorts of animals clung to the remnants of rainforest, that retreated to the edge of the continent.
This event brought two entirely different suites of species into near contact. The zone between them is located in the Malay archipelago and is called Wallace's Line, after the English naturalist Alfred Russel Wallace. The distinction remains today because migration in both directions has been difficult due to water barriers between islands. The migration of the island continent towards the equator has controlled the development of the Great Barrier Reef. By 17 million years ago, the northern tip of Australia came to lie fully within the zone favouring the luxuriant growth of coral reefs. As the collision between Australia and Southeast Asia continued, inter-island distances decreased further, permitting some exchange of plants and animals by island hopping. Rodents reached Australia. Then, during the last 2 million years, the development of vast ice sheets, mainly in the northern hemisphere, repeatedly caused sea levels to drop by about 150 metres. Inter-island barriers diminished further. 10 million years ago, the Australian rainforests had started to give way to savanna grasslands and deserts over large areas of the continent. The last 2 million years have been marked by the repeated rise and fall of sea levels as global temperatures fluctuated. It was during these glacial periods that the continental shelf surrounding Australia became exposed and the Arafura Sea emptied, exposing land bridges that linked the mainland to New Guinea. In the same way, the Southeast Asia Peninsula extended to include much of Indonesia. It was across this land bridge that new species, including a new genus, Homo, appeared in Australia. We shall never witness it, but if, as seems likely, the present direction and rate of movement continues for another 20 million years, the entire continent will enter the tropical climatic zone. Australia will become part of the Southeast Asian landmass and finally cease to be the island continent.
In Western Australia. Zircon crystals are tiny fragments of zirconium silicate, extremely small. And when zirconium silicate first crystallises, it takes in uranium. That uranium then decays to lead, and we can measure the uranium and the lead and work out the age of the crystal. And this is called the shrimp iron microprobe. What we do is we mount the zircons up and we put them into the instrument where they are ready for analysis. We take them down into the main receiving chamber, and then we fire a high energy beam of charged particles at that target. When the particles hit the target, they remove small amounts of material, and that material is then accelerated at high voltage into the rest of the machine, and that it can be measured for chemical and isotopic composition.
Were produced by volcanic eruptions from the partially molten mantle. Meanwhile, the interior of the planet was forming. Iron and nickel sank to the core, while the lighter elements rose to the surface.
We know the types of rocks that make up the Earth's mantle because some particular types of volcanoes bring up fragments of the mantle. For example, this is a fragment of the Earth's mantle which has come from 60 kilometres below the surface of the Earth from Western Victoria. The black part around the outside is some of the frozen magma that has brought it to the surface. It's very important to do this type of research because these rocks are a unique window into the composition of the interior of the Earth. Some samples represent the pristine composition of the Earth as it formed from the solar nebula 4.6 billion years ago, and others
have been uplifted, eroded and redeposited. Its climate has varied dramatically, and it has seen a continuously changing procession of life forms as evolution has altered them into ever more varied and complex types. With the passing of time, it has developed the unique heritage we enjoy today. The origin of our planet was so long ago that much of the evidence for it has been lost. Born like the other planets from the gas and dust of the early solar system, planet Earth gradually cooled and was soon covered by oceans of molten rock and rafts of solid matter. Condensation of the surrounding gas cloud produced water. The rocks of the original crust shaped by the collision of previously separate areas of continental rock and has moved across the surface of the globe twice to both the north and south polar regions. Australia has experienced enormous changes. Its rocks have crumpled, melted.
Examples, such as this particular one, give us an indication of the sorts of changes that have happened to the Earth throughout its geological evolution throughout those 4.6 billion years. This is a view through the microscope of thin sections of rocks which make up the Earth's mantle. These thin sections give us a glimpse of the microstructures of the rocks that make up the mantle, of the forces that they've been subjected to throughout geological time, and the bright colours help us to determine the types of minerals that make up these rocks.
Modern methods first developed at the Australian National University have enabled us to date some of the minerals contained in these early rocks.
The oldest known terrestrial material is zircon crystals, which are found in this sedimentary rock from Mount